Hi children and viewers. In this video I am going to explain most important very short answer questions in the chapter of electric capacitance and potential. Clear? Very important questions. Here very important questions means those questions are asked in previous examinations so many times. That's why we will consider them as most important questions. So based upon the previous examination papers, these are the important questions in the chapter of electric potential and capacitance. So let's go for that. Children, on board we have some questions are there. This is the fifth very short answer question in textbook. Fifth very short answer question in our textbook, that is 3 capacitors of capacitances 1 microfarad, 2 microfarad and 3 microfarad are connected in parallel. What is the ratio of charges and what is the ratio of potential differences? This is the first question, most important question. 3 capacitors of capacitances 1 microfarad, 2 microfarad and 3 microfarad are connected in parallel. What is the ratio of the charges and what is the ratio of potential differences? That is the first question, children. So children, how is the connection? Parallel combination. That's why I am going to draw here. This is the first one, C1 capacitance, and this is C2 and this is C3. How they are connected? They connect in parallel. So again this will be given some battery. So this is the parallel combination C1, C2 and C3. So children, you have to remember 2 points in this case. In parallel combination, which physical quantity is constant, and in parallel combination which physical quantity can changes. So here how they are connected in parallel combination, C1, C2, C3 are connected in parallel. That's why in the parallel combination the potential across every capacitor must be same as potential across the battery. That's why in parallel combination potential difference is constant. So clear, children? And next thing here, the charge available on the capacitor should be different, because here what you have to say, there should be splits into number of paths. The charge supplied on the capacitor should be moving in the different paths. So that's why here the charge will be varies from capacitor to capacitor, but the potential across the every capacitor is same. That's why here, children, so already we know that what's that, C is equals to Q by V. C is equals to Q by V. This is the expression for capacitance. Clear? So C1, C2, C3 are in parallel connected to the battery like that. So first what you find, what is the ratio of charges? What is the ratio of charges? That is the first thing here. C is equals to Q by V. From that what to write? Q is equals to what, children? CV. Q is equals to CV. So ratio of charges. Now I am writing that Q1 is to Q2 is to and Q3. Clear? Q is equals to CV. That means here Q1 is what? C1 V1 and Q2 is what? C2 V2 and Q3 is what? C3 V3. That's why here C1 V1 is to and C2 V2 is to C3 V3. Clear? So children, what I told you, in this combination, parallel combination, the potential is same. That's why all right, C1 is to C1 V is to C2 V is to C3 V, because V1 is equals to V2 is equals to V3 is equals to V. Clear? In parallel combination, potential across the every capacitor should be same. That's why here what right, C1 is to C2 is to C3 V. That's why I write, children, here C1 is to C2 is to C3. That is equals to what? C1 is what? 1 microfarad. C2 is what? 2 microfarad, and this is what? 3 microfarad. That's what, right? 1 is to 2 is to 3. So it is the ratio of charges. Ratio of charge, what it is? Q1 is to Q2 is to Q3. That is equals what? 1 is to 2 is to 3. So this is the ratio of charges. Got my point, children? So this is the first thing. What is that? Ratio of charges. So children, ratio of charges, how we can write? C is equals to Q by V, Q is equals to CV. Then ratio of charges we are writing Q1 is to Q2 is equals to Q3. That is equals to C1 V1 is to C2 V2 is to C3 V3. In parallel combination, the potential differences are same. That's why V1 is equals to V2 is equals to V3 is equals to V. Then what, right? C1 V, C2 V, C3 V, V cancel. Then what you get? Q1 is equals to Q2 is equals to Q3, nothing but C1 is to C2 is to C3. So C1 value is 1 microfarad, C2 value is 2 microfarad, and C3 is 3 microfarad. That is the ratio of charges. Now second bit, children. What is that? What is the ratio of potential difference? What is the ratio of potential difference? I already told you. What's that? In here only I am writing. In parallel combination, V1 is to V2 is to V3, nothing but what, right? V is to V is to V, because V1 is equals to V2 is equals to V3 is equals to V. Here what is V1? Potential difference across the first capacitor. And what is V2? Potential difference across the second capacitor. And what is V3? Potential difference across the third resistor. And what is V? Applied potential. Applied potential. That's why here the potential across the every capacitor should be same as the applied potential. That's why here I am writing V1, V2, V3 equals to V. That means V1 is to V2 is to V3 means what? V is to V is to V. That means 1 is to 1 is to 1. So this is the, children, the ratio of charges in parallel combination of 3 capacitors, and this is the ratio of potential differences in parallel combination. Children, same type of questions will be asked in competitive exams also. Sometimes here the value should be different. Not only every time 1 microfarad, 2 microfarad, 3 microfarad. The value should be different. So in different problems they will give different values also. That's why. So you have to assume that what is the formula and how we can find out the ratios. That's the important. Clear? So this is about the first, children. And second question is children, here that is on the board again. Children, again same thing here, the same capacitors, here again same, that is what? 3 capacitors of capacitances 1 microfarad, 2 microfarad and 3 microfarad are connected in parallel. So that is, in previous problem the same question should be in like this, it is in series. Clear? So that is the question now here, children. That should be mentioned as the 6th very short answer question in your textbook. Clear? 3 capacitors of capacitances 1 microfarad, 2 microfarad and 3 microfarad are connected in series. What is the ratio of charges and what is the ratio of potential differences? So this is the question now, children. This is also very important. So that is also asked so many times in examination, public examinations. So here, children, here this is the C1 and this is C2 and this is C3. First capacitor of capacitance C1, second capacitor of capacitance C2 and third capacitor of capacitance C3. So they are connected as in series as shown in figure. So I already explained everything in another video, series combination, parallel combination of capacitors. Children, here what we know, V1, V2 and V3. Clear? In series combination, what we take? V is equals to V1 plus V2 plus V3. and Q1 is equals to Q2 is equals to Q3 is equals to Q. So we have to remember these conditions, children. Clear? In series combination, the potential supplied by the battery should be nothing but algebraic sum of individual potentials across the every capacitor. Clear? V1 plus V2 plus V3. V1 is potential difference across the first capacitor, and V2 is second one, and V3 is third one. And in this case, you have to remember the charge can be moved in only one path. The charge can move in only one path. That's why the charge available on the every capacitor will be same. This is plus Q and this is minus Q, plus Q and minus Q, plus Q and this is minus Q. So I clearly explained about the series combination and parallel combination of capacitors in different videos. So I already uploaded it. So you must watch them in this playlist. So children, now here first thing, what is the measure? What is the ratio of charges? What is the ratio of charges? Just now only I told you Q1 is equals to Q2 is equals to Q3 is equals to Q. That means what? Here the first thing, ratio A, this is A, ratio of charges. Q1 is to Q2 is to Q3. That is equals what, right? Q is to Q, because Q1 is equals to Q, Q2 is equals to Q, and K3 is equals to Q. Then what are children? Here 1 is to 1. So this is the ratio of charges. And now children, second one is what? Ratio of potential differences. Children, we have formula is there. C is equals to what? Q by V. C is equals to Q by V. From that, what, right, children? V is equals to what, right? Q by C. V is equals to Q by C. Clear? C is equals to Q by V and V is equals to Q by C. From that, what will be, children? V1 is equals to Q1 by C1 and V2 is equals to Q2 by C2 and V3 is equals to Q3 by C3. Clear, children? So just look at this one. Clear? We know that C is equals to Q by V and V is equals to Q by C. So by using that, what, right? V1 is the potential difference across the first capacitor. Q1 by C1, second is Q2 by C2, and third one is Q3 by C3. Now we have to substitute here potential ratios. What is that? V1 is to V2 is to V3. What is V1? Q1 by C1 is to Q2 by C2 is to Q3 by C3. That means what? Here I am writing Q1 by C1. So children, I hope you understand this one. Series combination. We need some space, that's why I am arranging the diagram. So children, here V1 is to V2 is to P1 is to V2 is to V3 is equals to what, children? Q1 is equals to Q, Q2 is equals to Q, Q3 also Q. That's why I'm writing here Q by C1 is to Q by C2 is to and Q by C3. Then what we get, children? 1 by C1 is to 1 by C2 is to 1 by C3. That is V1 is to V2 is to V3. Clear? So what is the C1 value? 1 microfarad. That is equals to 1 by C1. C1 is what? 2 microfarad. Sorry, 1. And 1 by 2 microfarad and 1 by 3. 1 by 1, 1 by 2, 1 by 3. So this is the ratio of potentials. V1 is to V2 is to V3. So children, if you want to go for one more step, how we can write? V1 is to V2 is to V3 is equals to what, right, children? 6 is to 3 is to 2. 6 is to 3 is to 2. So this is the ratio of potentials in the case of series combination, children. So this is the second one. So generally most of the students will get confusion. Why? Because the problem will be same. For parallel combination, somebody write series combination answer. For series combination, they will write some parallel combination. So why they are getting confusion? Simply when they have no idea about the knowledge about the concept, then they will do mistakes. So when we have clear idea about the series combination, parallel combination, so we can easily substitute those values. In series combination, charge is constant, potential varies. In parallel combination, potential is constant and charge should be varies. So if you have about that one idea about that one, simply you can answer the questions. And children, now third question is there on board. Here there is one third question for us. That is also most important. It is asked so many times. And here these questions are very preferable in competitive exams also. That's why you have to prepare them. What happens to the capacitance of a parallel plate capacitor? So what is mean by parallel plate capacitor and what is the working principle? Already clearly explained in the one of the video. So you must watch it. So children, here now, what happens to the capacitance of a parallel plate capacitor if the area of the plates is double? So children, you must to do the answer, you must know about the what is the working principle of a parallel plate capacitor. So we have one formula is there. C is equals to epsilon naught A by D. C is equals to epsilon naught A by D. So this is the working principle of a parallel plate capacitor. Clear children? C is equals to epsilon naught A by D. So here epsilon naught is the permittivity and free space. A is the area of the plates and D is the distance between the plates of a capacitor. So here simply C is equals to epsilon by A by D. In this case, what he was asking, what happens to the capacitance? So what happens to the capacitance of the parallel plate capacitor if the area is double? That means in that problem he was asking about the just capacitance and area. If area is double, what happened to the capacitance? So in that question he was raising relation between capacitance and area only. So that means what? Epsilon is constant, D also constant. That's why we will write here C is proportional to A. Capacitance of a parallel plate capacitor is directly proportional to the area of the plates. So that's why children, what you have to write? From that we can write C1 by C2 is equals to A1 by A2. Now this is the formula. C1 by C2 is equals to A1 by A2. So children, so already what you are saying here, we are writing A1 is equals to A1 is equals to, here let initially area of the plates of capacity is what? A. Now what you are saying, area of the plates is double. That means I am taking A2 is equals to 2A. Clear? C1 is equals to A and A2 is equals to 2A. Then substitute here C1 by C2 is equals to A1 is what? A and A2 is what? 2A. Then what do you get? C1 by C2 is equals to 1 by 2. Then C2 is equals to 2C1. C2 is equals to 2C1. Cross multiplication. 2 into C1 and 1 into C2. Then what do you get? C2 is equals to 2C1. C1 is what? Here initial capacitance and C2 is what? Capacitance after increasing the area. That's why here the capacitance should be double. When area is double, capacitance also double. Capacitance also double. That means simply when we have idea about the formula, you can easily do this one. C is equals to epsilon A by D is the working principle of a parallel plate capacitor. Then what right here is to comparing the C and A only. That's why our relation is there. C is proportional to A and C1 by C2 is equals to A1 by A2. Then initial area is A and after increasing the double the area, A2 is equals to A. we are substituted, and finally what we get, C2 is equals to 2C1. Clear? So next we have one more question. Okay children, we have two more questions on the board. Look here. These questions are seems to be same, but both are different. Can there be electric potential at a point with zero electric intensity? Can there be electric potential at a point with zero electric intensity? That means E is equals to 0 and V is not equals to 0. Clear? At that point electric field is 0 but the potential is not equals to 0. For that situation, is there any example? If it is, give example. That's the first question. Can there be electric potential? Is there any electric potential at a point with zero electric intensity? At one particular point electric field intensity is 0 but potential is not equals to 0. Is it possible or not? If it is possible, give example. Here, can there be electric intensity at a point with zero electric potential? Reverse of this one. Can there be electric intensity at a point with zero electric potential? Zero electric potential. That means E is not equals to 0 and V is equals to 0. In this case, electric field is 0, potential is not equals to 0. In this case, E is not equals to 0 and V is equals to 0. Clear? So that's why while you are writing the answer in the public examinations, you must be read carefully. So don't confuse. Clear children? Children, already we know that potential due to a point V is equals to 1 by 4 pi epsilon naught Q by R. This is the electric potential due to a point. And equation. And electric field intensity is what? 1 by 4 pi epsilon naught Q by R square. Clear? This is the electric potential due to a point, and this is the electric field intensity due to a point charge. Clear? Electric field due to a point 1 by 4 pi epsilon Q by R. Electric field intensity due to a point 1 by 4 pi epsilon Q by R square. Already we know that potential is a scalar quantity and electric field intensity is vector quantity. What is that? Vector quantity children. So I am not going to prove these things, simply I will give examples. So here first I am going to this topic here, don't focus here, just you have to focus this part. Can there be electric potential at a point with zero electric intensity? So that is the question asked for us. So then you have to say simply answer is S. First you have to write answer is S. Can there be? S, it is there. What is that? Electric potential at a point with zero electric intensity. Yes, there be electric potential at a point with zero electric intensity. So that what it is? S. For that 1 mark is avoided. Okay. So when we are taken two similar charges, either it is both are plus or both are negative. Plus Q or minus Q. Clear? Plus Q we are taken or minus Q we are taken similar charges. When they are similar charges are separated by some distance, at a midpoint electric field intensity is 0 and potential is not equals to 0. Clear? So answer is what? S. When two similar charges are separated by some distance, at a midpoint of those two similar charges, electric field intensity is 0 but potential is not equals to 0. Clear? And now we are explained in case of Gaussian applications. Gauss law application. In the Gauss law applications, I clearly explained this one. In case of a charged sphere, inside the charged sphere at a point electric field is 0 because the charge is 0 inside the sphere. In case of a charged sphere, the charge is available on the Gaussian sphere or charged sphere. Inside there is no charge. That's why electric field intensity is 0. E is equals to 0. And now here, but electric field intensity is 0 even though there is some potential here, that is V, because the charge available here it is, that is Q. For example, Q is the amount of charge on the sphere at particular distance. For example, I am taking this distance R. At this point, there is some potential, because the potential due to a point is what? V is equals to 1 by 4 pi epsilon Q by R. Clear, children? So that's why in case of a charged sphere, inside the sphere there is no electric field intensity, but there is some potential is there. V is equals to 1 by 4 pi epsilon Q by R. The charge is available on the sphere. That's why from that particular distance there is some potential. So that's why you have to write this answer like that. Can there be electric potential means what? Yes, there is a point electric potential at a point with zero electric intensity, where in the midpoint of the two similar charges electric field is zero but potential is not zero. And in case of a charged sphere, inside the sphere electric field is zero but charge is there on the sphere. That's why there is some potential is there. Now this is the one type of question. Our next question here: can there be electric intensity at a point with zero electric potential? Give an example. Clear? S. In this case also first you write S. For answer that is what? S. So even though don't know, simply you can write S. You will get 1 mark. Here, can there be electric intensity at a point with zero electric potential? S. So where means when we are taken a dipole, at the middle of the dipole the potential is zero. So I uploaded one video for that one. Find out the electric field potential or electric potential at a point on the equatorial line. I clearly explained already. That video is uploaded in this playlist. You must watch it. So electric field potential due to a point on the axial line, on equatorial line, I uploaded one video for that. So you just watch it. So children, here this is the dipole. At the middle of the dipole point, what you have? Electric field is not equal to zero but potential is zero. So in both cases you have common similarities, as both are possible. That's why you have to write first thing is S, here also S. For this 1 mark should be awarded, and for remaining examples 1 more mark is awarded. So children, these 5 questions are very important for public examination point of view. That's why you must watch them and you must prepare the notes and you have to remember those formulas. Okay children, we will meet in the next video with some other interesting topic. Bye, take care.